Okay, so let's take a look at this idea of how we deal with categorical variables. And one of the real keys to deciding what kind of statistical tests to perform is what kind of data are you collecting? Okay, the data is really what drives the particular test that you're going to be using. A lot of times we get students come back to us because they're working on a capstone or a project or something like that, and they have like a whole bunch of data they've collected, and they sit down and want to know if we can give them some help on deciding how to analyze the data. That's really the wrong time to be discussing how to analyze data. You really should be considering how you're going to analyze the data before you actually collect it, because eventually you're going to have to get to that point. So you don't want to have gone through a lot of work collecting data and then maybe not having uh, 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 collected the type of data or the amount of data that you really need to move forward. So if you guys are considering that, if you're ever in that situation, maybe talking to us before rather than after you collect the data might be a good idea. But that brings us up to the point that, like, up till now, we've been spending a lot of time looking at numerical data. In other words, descriptive statistics for scalar or numerical data like blood pressure, BMI, weight, and so on and so forth, something that's on a number scale. Okay, so and in those tests, we looked at the confidence interval. We learned how to employ the t-test, which looks at the difference between two means, whether or not they're far enough apart that you can safely say within your limits of probability. You can say that the populations of the two means are different, and so on and so forth. So now we're going to be taking a look at another kind of data, which is categorical data. And in categorical data, we have information that is not expressed as maybe expressed as a number in SPSS when you enter data into SPSS, but really represents a name or a category. So, for instance, could be gender, could be male or female. Okay, male or female could be represented by numbers one and two, but it's really still categorical data. So, what I'm going to do is I'm going to take a look at this problem, and we're going to talk about how to solve these kinds of problems with categorical data. Now, this actually, if you look at the schedule, this actually was intended for after the exam two, but I really wanted to get this in a little earlier because so much of the data that you'll be using or have available to you in the New York City Community Health Survey that we're giving you to work with for uh, uh, for your projects and so on and so forth, unless you find some other data source you want to work with. So much of that data is categorical data rather than numerical data. So you won't be able to use the t-test or chi-square, or excuse me, the t-test or the confidence interval and so on and so forth to solve those particular problems or to work on your project. So you need another tool for categorical data. Okay, so as we discussed in the lab, let's take a look at the problem. Data is accumulated for bicycle accident victims at a local emergency room. Data is collected on whether a head injury was sustained in the accident. This is pretty timely, right? Because plenty of stuff going on in New York City with bicycles right now. And if the bicyclist was wearing a helmet, this data is reported in the data set injury.sav. Perform a hypothesis test to determine if wearing a helmet reduces the likelihood of head injury in bicycle accidents. Now, what we're really looking for is whether or not a helmet is associated with the risk of having a head injury if you get into an accident on a bicycle. Okay, so let's open up this data and see what it looks like. Let me make sure I have it available to me here. Let's see. Not in that one. I might have to download it from Blackboard. Oh, here we go. Actually, I called it head injuries. Let me. Yeah, you should correct that. I'll correct that later on. But yeah, the file is actually called head injuries. Hopefully, you guys figured that out. Yeah. Oh, no, it is headinjury.com. Okay, good. So I'm going to look at it in Excel first. Okay. Okay. Open a repair. Hopefully, I'll see it. Okay. Didn't like that file. Okay, how about this version of it? Okay, so here's what the data looks like in Excel. Oh, nope, that's the height data. Well, I guess I'm going straight to the SPSS file. Okay, let's give it a moment. Okay, there we go. Okay, it came up in the variable view. I'm going to switch back over to the data view. And we see a series of numbers, ones and twos, that represent the variable head injury and the variable helmet. Let's go over to the variable view and see what those variables mean. Okay. Well, let's see. The variable head injury. Actually, that variable head injury, if I look at the label, that variable head injury is short for sustained a head injury. And the values that you might get are one represents yes, a person sustained a head injury, and two represents no, they didn't sustain a head injury. Okay. The variable helmet similarly has two values. Okay, I know it ahead of time even before I clicked in. And that's yes or no, they were wearing a helmet or they weren't wearing a helmet. So we have two variables, each with two values. And we know that that's going to be it. We're going to be able to construct a 2x2 table. Okay, so I'm going to go up here to Analyze. I'm going to go up to Descriptive Statistics. Since we're going to start off by creating a table of some kind, I'm going to go into crosstabs. Okay, so that's going to create our crosstabs tables or contingency tables. Now, I'm in the habit of putting the exposure in the rows and the outcome in the columns. For instance, exposure might be asbestos, and the outcome might be lung cancer. So I would put the exposure asbestos, yes or no, in the rows, and outcome lung cancer, yes or no, in the columns. So let's see, wore helmet, that's the exposure, I think, is wore a helmet, whether the person wore a helmet or didn't wear a helmet. And the outcome is whether or not they sustained a head injury. Okay, so now I'm going to go into these tabs and I'm going to look at them, and I actually can do a statistical analysis right away. But I just want to see what data we're dealing with. I want those ones and twos summarized for me. So I'm just going to click off observed for now. And it's going to create a table of observed values for me. Okay, here we go. Oops. There's our output window. Narrow it up so it comes up to the top. Okay, here's our output windows. How many people were in this study? Well, there was 793 people that went to emergency rooms after an accident on a bicycle. And as it happens, 147 had been wearing a bicycle helmet, and 646 had not been wearing a bicycle helmet. There were 235 with head injuries. There were 558 that did not have head injuries. Okay, that had some other injury. Okay, so the thing is that the actual breakdown of whether or not a person sustained a head injury or didn't sustain a head injury based on whether they were wearing a helmet or not may be happening at a different rate. You may be sustaining head injuries at a different rate. So let's take a look at that. 17 out of 147 people that were wearing a helmet sustained a head injury, and 218 out of 646 that weren't wearing a helmet sustained a head injury. So just off the top of my head, it looks like you're more likely to sustain a head injury if you're not wearing a helmet, right? So maybe I want to take this data now and I want to find a way to describe what this is telling us. So even before we collected this data, we had a pretty good idea that wearing a helmet would be protective in terms of head injuries, right? So maybe before I collected this data, I might have said to myself, well, let me set up a hypothesis. Let me do a hypothesis test. Okay, so anybody want to propose a hypothesis for this study? What might be our null hypothesis for this study? Remember, the exposure is wearing a helmet or not. Can I entice one of you guys into proposing a null hypothesis? Okay, that wearing a helmet or not wearing a helmet will have equal head injuries. I like that. That's good. I might phrase it a little bit differently to make it a little bit more general. I might say H null. My null hypothesis would be that there's no association between helmet wearing a helmet and head injury. Okay, I like that because it starts out with the assumption that it doesn't matter if you're wearing a helmet or you are wearing a helmet. My alternative hypothesis, alternative, H alternative, might be there is an association between helmet wearing and head injury. Okay, notice I didn't propose whether or not it increases the rate of accident, makes it more likely. No association, right? There is an association. There's no association. Great, thanks, Marnie and Susan. I start out with the null hypothesis, which is always that it's equal or there's no association, or and so on and so forth. And I want to prove that I can reject that with less than 5 in this case, because I think I said alpha equals I said alpha equals 0.05, and I didn't mention the level of certainty that we want. But you did notice I mentioned 95% confidence interval, so I think you can probably generalize that to an alpha error of 0.05. We want less than 5% chance of being wrong if we reject the idea that there's no association, if we reject the null hypothesis. Okay, so that's our objective now. We provided our null, an alternative hypothesis. Let's go back and take a look at our data. So this is the data that we observed. Okay, now if I wanted to know, gee, does this represent what I would expect to see if there's no association between helmet wearing and head injuries? Well, we can actually have SPSS. In this problem, we're going to have SPSS do this. And the next problem, we're actually going to calculate it ourselves. I'm going to have SPSS tell me, I'm going to go back in the crosstabs and cells, and I'm going to ask it to give me the expected values. Okay, and I'm going to click OK. SPSS calculates what we would need to represent the same rate of injuries in people that wore a helmet or people that didn't wear a helmet. So let's take a look at this. Well, we experienced far fewer in real life, and the observed values were far fewer than what we would have expected in 147 accidents. In the meantime, when we look at the people that didn't wear helmets, we saw that they experienced more injuries than we would have expected them to have injured. Now, the question now is the difference great enough for us to reject the null hypothesis, okay, that there is no association? Now, it looks like we see that there is an association and wearing a helmet is protective. However, these numbers don't always, when we do it in real life and we take a random sample, for instance, we don't always see exactly the value that we expect. So in other words, these numbers could be due to chance, or they could be due to an actual difference in the rate that people would get injured. Okay, so we have to make sure that these numbers are different enough that they're not likely to be due to chance. It doesn't have to be 100% certainty. It has to be at least 95% certainty. In other words, an alpha of 0.05. Okay, so at this stage now, I'm going to say to myself, let's calculate a chi-square value. Now, we did this in class, and the way we did it was we took the expected value minus the observed value squared divided by the expected value. Okay, and we got a number for this first cell. Okay, then we took the next cell and we said the observed value minus the expected value squared over the expected value. And again, we did that with each one of these 4 cells, and we added them together to find a chi-square value. Chi-square is represented by basically a capital chi, which is basically a large X. Okay, so I'm going to go ahead and have SPSS do that for me. Analyze, descriptive statistics, crosstabs. Okay, I'm going to go into statistics this time. and ask it to calculate the chi-square value for me. And I'm going to say OK. OK. And it calculates the chi-square value for me. The chi-square value turns out to be 28.255. There is another version of that formula where we subtract 0.5 from each one of the, before we square each one of those differences, before we square them, we subtract 0.5 and then square it. And it comes out to a smaller number, more conservative form of the test. I'm not going to have you do the continuity correction. I'm also not going to have you worry about the Fisher's exact test for now. We'll talk about that later on. But the Pearson's chi-square, which is the one we calculated, the simple one, is good enough for us. Now, the number of degrees of freedom represent, depending on how many boxes that we're dealing with in our crosstabs. If we were dealing with something that had was a table that had 2 rows by 4 columns, you can imagine the chi-square value, just by nature of having those extra columns, is going to be bigger without affecting the risk, the odds, or the risk of your having a rejecting the null hypothesis. Okay, so we know that the number of cells, the rows and the columns, will affect how big a chi-square that we need in order to reject the null hypothesis. Okay, well in this case, we got a null hypothesis of 28.255. We have 1 degree of freedom. The 1 degree of freedom is there because the degrees of freedom is based on the number of rows minus 1 times the number of columns minus 1. So that would be 2 rows minus 1 is 1, 2 columns minus 1 is 1, 1 times 1 is 1 degree of freedom. So we can use a chi-square table that represents 1 degree of freedom. So I'm going to pull up the chi-square table. Chi-square. Oops. Okay, let me pull that up. Okay, oops, don't need that. Here we go. Okay, so our chi-square value for 1 degree of freedom, that gives us a probability of exceeding the critical value, probability based on a critical value of 0.05, is 3.841. In other words, if we exceed the number 3.841 for a chi-square that has 1 degree of freedom, there's less than 5% chance that we would get that outcome by just randomly, if there's no difference between wearing a helmet and not wearing a helmet. So as long as we exceed that critical value, we can reject our null hypothesis. We know our probability of being wrong if we reject our null hypothesis, or having that outcome by chance, that bigger chi-square by chance, is less than 0.05. We don't necessarily know from just this one column how much less, but we know it's different enough that we can reject the null hypothesis. So in this case, since it's 28.2 or 3, we can reject the null hypothesis. Now, SPSS actually goes a step further, and it gives us the real probability of having this big a chi-square value, this big a difference between the exposures, having this big a difference, and having that happen by chance. And as it happens, it's less than 0.001. You see it as 0.000, but it's not really 0. It's really less than 0.001. So it's very unlikely you would get this outcome. So you could feel quite safe rejecting the null hypothesis. The real key here is that this needs to be greater than 3.84, and this needs to be less than 0.05 for you to reject the null hypothesis. Okay, so I want to go back here, and so our let's see. Actually, that should have been chi-square value, and the p-value. Let me well, okay, God, that's right. That needed to be fixed. Okay, that's the chi-square value and the p-value. Okay, report. You can. Okay. So next, it asks you to report the odds ratio for a 95% confidence interval. I'm actually going to take another look at that, and I'm going to say report the relative risk or risk ratio and the odds ratio. Okay, so let's go back to our data. And now I'm going to go back up here to analyze descriptive statistics crosstabs. I'm going to go into cells. I'm going to turn off this expected values because we don't need it right now. And I'm going to ask SPSS to give us percentages by rows. And I'm also going to go up here in statistics, and I'm going to ask it to calculate risk. And I'll say OK again. Okay, so let's take a look at what we have now. Now, it took away the expected values. Okay. However, it gave us something extra. It gave us the percentages by rows. In other words, 17 is 11.6% of 147. 218 is 33% of 646. Okay, so so really this is just 17 over 147, and this is 218 over 646. So I could say that the risk of sustaining a head injury if you have a bicycle accident and you're wearing a helmet is 11.6%. And the probability of sustaining a head injury if you're not wearing a helmet is 33.7%. So the relative risk is 11.6 divided by 33.7. In other words, it's about 1/3 as likely, you're about 1/3 as likely to sustain a head injury if you're wearing a helmet. Okay, now, had I organized this differently so that the not wearing a helmet was on top and yes was on the bottom, I can actually change or recode the variable so that happens, right? Recode the 2 into a 1 and 1 into a 2, so that actually happens. If this had been on top, it would have given me the inverse of that. In other words, 33 over 11.6. Not wearing a helmet is you're 3 times as likely to sustain a head injury. The way it's formatted here, where 1/3 is likely if you wore a helmet. They're really basically saying the same thing. 1/3 is likely to sustain a head injury. In other words, wearing a helmet is protective, gives us a decimal below 1. And if we formatted the other way, 33 over 11, it'd be 3 times. Your risk is 3 times as much if you don't wear a helmet. 1/3 is likely, or 3 times as likely. Same thing, except the opposite outcomes. Okay, so in fact, if I go down here, SPSS has actually calculated these values for me. The odds ratio for wearing a helmet and getting head injury is 0.257. Actually, it was, I guess, yeah. Oh, now hang on a second. Before I get to that, the relative risk was about 1/3, I said. And in fact, for cohorts sustained a head injury, the relative risk is 0.343. That's where relative risk is hidden here. Okay, and interestingly enough, for cohort no, I don't want to confuse you with that stuff. But right now, for cohort yes, that's our relative risk. You can see that that's our 11.6 over 33. Okay, so now on top of that, we have something else called odds ratio. And the odds is based on a different view of this data. So in other words, the odds are based on whether or not a person sustained a head injury versus not sustaining a head injury. So the odds of a head injury is 17 to 130, or 17 over 130. That's the odds of sustaining a head injury if you wore a helmet. The odds if you don't wear a helmet is 218 over 428. So if you calculate 17 over 130 and divide it by 218 over 428, that's your odds ratio. And that's what you have here, 0.257. The odds of your sustaining a head injury is 0.257 if you wore a helmet versus if you didn't wear a helmet. Okay, so we can say that we can reject the null hypothesis that there is no association and accept the alternative hypothesis that there is an association between wearing a helmet and head injury. One other piece of information that we can glean from this is if there was no difference between the rate at which people that wore a helmet had a head injury or didn't wear a helmet had a head injury, what would you expect the relative risk or the odds ratio to be? Anybody want to hazard a guess at what you would expect those numbers to be? One, exactly. You'd expect the same rate of head injuries for people who wore a helmet versus people that didn't wear a helmet. Okay, and let's go back down here to the odds ratio and the relative risk. Now, the odds ratio came up 0.257. We discussed how we got that. Okay, now we want to be certain, 95% certain, or less than 5% chance of being wrong, that is not that we didn't calculate that by chance. That in fact it's really one. So SPSS tells us the odds ratio, but it also gives us the confidence interval for the odds ratio as well. So we can see that the confidence interval, in other words, for the entire population of all bicycle riders and helmets, it tells us the odds ratio tells us that the true overall odds ratio for the entire population, we're 95% sure it's between 0.15 and 0.437. So that means that we're also sure that it's not one. In fact, that it's less than one. So indeed, it's protective. And also with the relative risk, we can see one is excluded from the confidence interval also. So that's more evidence that we can reject the null hypothesis. We have three different pieces of evidence to reject the null hypothesis. One of the nice things about the odds ratio and the relative risk is they give you an idea of how protective that the wearing a helmet is compared to not wearing a helmet, where the chi-square just basically confirms for you that you can actually reject the null hypothesis. Yeah, if there was no association, the odds ratio and the relative risk might not be exactly one, but the confidence interval would contain one. In other words, it might be from zero point 0.8 to 1.2. Okay, the odds. Let's say that the odds ratio were 0.9. It might be 0.7 and 1.2 or something like that. Okay, so the chi-square, if we wouldn't have been able to reject the null hypothesis, chi-square would have been less than 3.48. The significance would have been greater than 0.05. That's called also the p-value. Okay, the odds ratio and relative risk, their confidence intervals would not have excluded one. One would have been within the confidence interval somewhere. So those are all clues to the results on that. Okay, so I want to go on to the next one, where you actually do some real calculations on your own. I'm going to open up Excel. Unless I gave you, I don't know if I gave you that file. Shipyard workers, asbestos. Did I give you that file? Let me see. The document number 6 wasn't on Blackboard. I couldn't find the file on Black. Oh, okay. Well, you can make it up your own, right? Because, hang on a second, I'll make it up right now. I'm going to open up Excel. You actually could have done this even without Excel. Let me make this bigger so we can see it. Okay. Let me get that number here. Okay, so I'm going to say asbestos exposure. Oops. No asbestos. And let's see, lung cancer. And no lung cancer. Okay, so we got 12, 288. We got 42 and 2070. So that's a total of 300 people who were exposed, 212 people who were not exposed. Okay, so this is my now, are these my expected values or my observed values? Let's start with that. Anybody want to tell me whether these are my expected values or my observed values? Right, these are my observed values. We actually saw 12 out of 300 people that got lung cancer. Okay, so now in order to calculate the chi-square value, I now have to create another table which has my expected values. Okay, so this is observed. And now I'm going to have to create a table of my expected values. I know I made one up. I guess I didn't upload it for some reason. I'm going to just copy this and paste it here for starters. And then I'm going to delete these numbers. Okay. Okay, we know the total number of people that got lung cancer was 454. Total number of people that didn't get lung cancer was, let's see, 2000. I'll tell you what, equals sum. Don't have to strain my brain here. Okay, and the total number of people is equal to, oops. Okay, 2414. Okay, I'll put I'll put up a neater version of this, I think, too. Actually, let me just clean it up a little bit right now. I need this to be a little wider so I can get to the tools. Up 2412, you're right. Another reason I love Excel. If I had Excel do it for me. Okay, let me throw some boxes around this so we can see what we're doing here. Okay, and there's our crosstabs there in the middle. And here's our expected values are going to be in here. Okay, and I'll just put this back up here so we just, for completeness sake. Okay, so now how are we going to find out our expected values? Well, in order to find out our expected values, our presumption when we look at our expected values is that there's no difference between the rate at which people who were exposed to asbestos got lung cancer or not exposed to asbestos got lung cancer. So we expect that everybody in the population, everybody in the sample or the population got lung cancer at the same rate. So what we would like to know is what's the prevalence for lung cancer in this population? Anybody want to speculate on what the prevalence is? How would I calculate the prevalence here? Take a wild guess. Right. Well, in the entire population, 54, in the entire sample, 54 over 2412. Right, great, terrific, good, excellent. 54 out of the 2,412 people got lung cancer. That's the rate at which the population overall got lung cancer. So if we have 300 people that were exposed to asbestos, we would expect them to get lung cancer at the same rate as the rest of the population. So we would expect the number of people getting lung cancer being equal to 300 times their rate, the prevalence rate, okay, which is about 6.7 people. Okay, well, how about what number is going to go in there? Well, it's going to actually just be the difference between 300, right, and the number of people that got lung cancer, because the ones that didn't get lung cancer fill out the remainder of the 300. Well, how about the people that didn't get asbestos? People that were not exposed to asbestos, they're also going to get lung cancer, or we expect them to get lung cancer at the same rate. So this is going to be equal to 2112 times the prevalence for the entire sample or population. Okay, and again, this is going to be equal to 2112 minus 47. Okay, so that's our expected values. Now, if we wanted to calculate what chi-square is equal to, okay, in other words, chi-square, right? If we wanted to calculate what chi-square is equal to, we would take our observed values minus our expected values, square it, divided by our expected values. Our observed value minus our expected values, square it, divide by our expected value. Our observed value, and so on and so forth. In fact, SPSS has a function for this, equals chi-test. parentheses. And I'm going to use that instead of going through that rigorous calculation. Actual range, expected range. So the actual range is these four boxes. We'll put a comma after that. And the expected range is these four boxes. It's doing exactly the calculation I just described and that we did in class previously. So our chi-square, our chi-square comes out to be 0.02755. Now, that's not really our chi-square value. That's actually, it actually jumps a step. That's our p-value, our probability of being wrong if we reject the null hypothesis. If we want, we can actually calculate chi-square using another function, chi-inverse. Oops. Okay, where we put in the probability, comma, the degrees of freedom, which are 1, enter, and our chi-square value is 4.85. So we have some help from Excel in doing this particular problem. So let me ask you this. If I have a chi-square value of 1 degree of freedom, 4.85, can I reject the null hypothesis that there's no association between asbestos exposure and lung cancer? Opinions? Can I reject the null hypothesis? Yep, I sure can. And what's my p-value? Is my p-value less than 0.05? In fact, the probability of being wrong, if I reject the null hypothesis, probability of getting this big a chi-square value just by chance, not by an actual difference in the rate that people got lung cancer, is about 2%, about 2 or 3%. So it's less than 5% chance of getting being wrong if I reject the null hypothesis. Okay, let me ask you one more. Well, while we have this open, what is the what's the what are the what's the risk of getting lung? I'm going to tell you this. I'll do it myself. What's the risk of getting lung cancer if you have asbestos? The risk is equal to 12 divided by 300, and the risk if you're not exposed to asbestos is equal to 42 divided by 2112. So the risk is 0.01. So 0.01 to 0.02. So what's the relative risk? The relative risk, or the risk ratio, is equal to 0.04 divided by 0.019. And our expectation here is that if there's no difference in risk, the relative risk is going to be equal to 1. And in fact, the relative risk is equal to 2. You're twice as likely to, your risk of getting lung cancer if you're exposed to asbestos is twice as likely as if you're not exposed to asbestos. Okay, so now, what about the odds ratio? What are your odds of getting lung cancer if you're exposed to asbestos? Somebody tell me what the numbers are there. Okay, what two numbers am I going to put my odds for people that are exposed to asbestos? Okay, 12, great, 12 over 288, good. And my odds for people that are not exposed to asbestos is, come on, help me out here. Good, excellent, 42 over 2070, I think, right? 2070, is that right? Yep. Okay, so my odds ratio, and again, this is another situation where if there was no association between asbestos and lung cancer, we would expect the odds ratio to be equal to 1. So it's equal to this number over this number, and it's equal to 2.05. Very similar to relative risk, but it's a slightly different angle at looking at how to express the difference in risk for these two groups. Okay, so I'll make sure that there's a version of this spreadsheet uploaded to make it a little easier to fill out. But you could actually get this. You could actually do this on your own. I guess I should put lung cancer. Right, no lung cancer over there, and do the same thing down here. Okay, and I think and you have the prevalence and you have the rest of this, and I'll add on the odds ratio. Now, the only thing we didn't calculate here, because it involves a little bit more complicated calculation, it's actually not anything that you haven't done already. It involves calculating. See, these are proportions, right? The odds and the risks are proportions, right? So you could, if you wanted to, based on those numbers, the proportions that they represent, you could calculate the confidence intervals for the odds ratio and the relative risk. We're not asking you to do that. On that end, you can actually depend on SPSS to calculate that for you. Okay, and in fact, if we had the data organized that way, you could have inputted this into SPSS and all 700 of these people into SPSS and actually done a similar analysis in SPSS. In this case, we actually gave you the summarized data rather than the actual raw data, which represented all 2,412 people, whether or not what their health status was, lung cancer, and what their asbestos exposure were. Those two columns for two variables. Now, technically, there is a way for you to use this summarized data. When we move forward and start talking a little bit with SPSS, there's a way for you to recreate this data file without having to put in 2,412 people so that you can evaluate it in SPSS, even though it's summarized data and not the raw data. Okay, but we'll worry about that going forward. You're not going to have to worry about that for the exam. Okay, so at any rate, you guys, I think you pretty well know since from the first exam kind of what to expect. It'll cover all the material since we took the first exam. You should review the PowerPoints because there'll be the problems will be very similar to what you see here. There will be some multiple choice or fill-ins and so on and so forth that will test your knowledge of some of the material that was in the PowerPoints as well.